Now, number 3 says iron plus 2 and iron plus 3 ions are able to form a variety of complexes with different species. Define the complex. We say that the complex is a compound formed when ligands donate their lone pair of electrons to a metal ion to form dative bonds, with it. So this is the definition of a complex. It's when ligands donate their lone pair of electrons to a central metal ion to form dative bonds with it. Okay, so they said here, table 3.1 gives some details of different complexes of iron plus 2 and iron plus 3. Complete the table. So here they said that here we have for the first complex E, the ion Fe plus 2, the ligand is ammonia, the coordination number is 6. We know that the coordination number is the number of bonds that are formed between the ligands and the metal ion. So the formula and charge of the complex, we have Fe, and since the coordination number is 6, it means that 6 ammonia molecules reacted with the iron, donated their lone pair of electrons to it. And so as the ammonia is a neutral ligand, so the positive 2 charge of the iron plus 2 remained. Now here we have FeCl4 minus 2. So this means that here we have the chlorine minus 4, because we know that every chlorine is negative 1, which means that the charge on the iron here is positive 2. So this means that we start with iron 2 positive. And since 4 chlorides are formed here in this complex, it means that the ligand is the chlorine atom. And here, since 4 chlorine atoms bonded to the iron, so the coordination number is 4. For the last one, we see that the positive charge here is positive 3, and we know that the ethylene diamine ligand or ethane 1,2-ethane diol ligand is neutral. So this means that here we start with the iron 3 positive, and the ethylene diamine is the ligand. And the coordination number here is also 6, because the ethylene diamine is a bidentate. And since it is bidentate, it means that it will donate lone pair of electrons through 2 nitrogen atoms. You remember that the ethylene diamine is like this, has this structure. And this means that it can donate 2 lone pairs to the metal ion instead of only 1. So that's why it's called bidentate. And since we have 3 of them, this means that there will be 6 coordination number. Number 3 says complete figure 3.1 to show the splitting of d orbitals in a tetrahedral complex. We know that in an octahedral complex, the d orbitals split into 2 higher and 3 lower energy levels, but in a tetrahedral complex, the opposite takes place. And so we'll see that if we start with 5 d orbitals, they will split into 3 above and 2 lower d orbitals. It's opposite to what happens in the octahedral. Here it says table 3.2 gives details of some complexes of iron plus 3. So here we have FeH2O6 plus 3. It has a violet color, and the value of the K stability is 1. The iron H2O5 SCN plus 2 is red. The K stability is 1.4 times 10 to the power 2. The iron H2OF plus 2 colorless. The K stability is 2.4 times 10 to the power 5. Explain the reason for the difference in color of the two complexes, FeH2O6 plus 3 and FeH2O5 SCN plus 2. Now, when we look at this complex, we will see that the thiocyanate ion has a -1, and we have 5 water that is neutral, which means that the iron here has the same oxidation number as that present here in the hexaaqua iron 3 type. So this means that the only difference here is the type of the ligand that is bonded to the iron plus 3. So when they say explain the reason for the difference in color, we say that different ligands, split the d orbitals of iron plus 3. Different ligands split the d orbitals by different energy gaps, which requires different frequencies of energies, which requires different frequencies which requires different frequencies of energy to excite or to promote the electron from a lower to a higher energy level, And of course, we know that we see the complementary color. So this means that different ligands will split the d orbitals by different energy gaps, which requires different frequencies of energy to excite the electron from a lower energy level to a higher energy one. And so, of course, we get different complementary colors are seen. So here we can say that different complementary colors are seen. So different complementary colors are seen. Now they said here, write an expression K stability for the iron H2O5 SCN plus 2. So of course, this compound is formed when the iron H2O6 3 positive reacted with the thiocyanate ion. It formed the iron H2O5 SCN plus 2. And of course, there will be a water molecule that comes outside. So to write the expression, so the K stability is equal to the concentration of the product, which is the Fe H2O5 SCN positive, divided by, of course, this is the concentration of this complex, divided by the concentration of the Fe H2O6 positive times the concentration of the SCN negative. And we do not include the water in our K stability expression because the water is in the form of a liquid. And all these are ions. It means that all of them are aqueous solutions. So whenever we have aqueous solutions with a liquid, we do not include the liquid in our K stability expression. Okay. Right. Let's see the next question. It says, use information in the table to calculate the value of the equilibrium constant Kc for the following reaction. So we have this reaction, And this means that the Kc value is equal to the concentration of the products times each other, which is the Fe H2O 5 F2 positive times the concentration of the SCN negative divided by the concentration of the Fe H2O 5 SCN 2 positive plus the concentration of the fluoride ion. So this is the Kc value. So they said using table 3.2. So from here, we see that from the table, we see that the K stability of the, we are going, okay, we have to write the K stability for each of these complexes and see which one of them, when we arrange it, we'll get the Kc value for the equation that they asked us about. So here for the first one, let us take these two. The K stability of the FeH2O5SCN is equal to, this is, let me write, this is 2 and this is 1, this is 3. So into the K stability is equal to the concentration of the FeH2O5 SCN 2 positive over the concentration of the Fe H2O6 2 3 positive times the concentration of the SCN negative, and the K stability for 3 is equal to the concentration of the Fe H2O5 F2 positive divided by the concentration of the Fe H2O6 3 positive times the concentration of the fluoride ion negative. And so we are going to arrange these two equations so as to get this one, the one above in the Kc expression. So we see that here we have the, if we look at the Kc value, we'll see that we have FeH2O5 F as a numerator, and the concentration of SCN minus also as a numerator. So this means that we can divide 3, the K stability 3 by K stability 2. So here we say divide K stability of 3 by K stability of 2. So if we divide them, this means that we will get Fe we get here Fe H2O 5 F positive 2. Then we are going to obtain this in the numerator. So we say times the concentration of Fe H2O 6 3 positive times the concentration of the thiocyanide ion divided by the Fe H2O6 3 positive times the concentration of the fluoride ion, and then times the concentration of this one that is present in the numerator, which is Fe H2O5 SCN 2 positive. And we'll see that this will cancel with that. And so we get the same equation here, which is the Fe2H2O5 F plus 2 times the thiocyanate divided by the fluoride times the Fe H2O5 SCN plus 2. And this means that we are going to divide, we said K stability 3, which is 2.4 times 10 to the power 5 over the K stability 2, which is 1.4 times 10 to the power 2. And so we get 2.4 times 10 to the power 5 divided by 1.4. So I got 1714.3 or 0.228, so it's 0.3. And as we see here that there will be no units for the Kc because we have three concentrations above and three concentrations below. So there will be no value for the units here for Kc. So this is the Kc value that we have to calculate. And it is with no units. It is with no units because the concentrations above are 3 and the concentrations below are also 3. So the mole per decimeter cube of every one will cancel with the other. And so there will be no units for the Kc value. They said a few drops of potassium fluoride are added to a solution of FeH2O6 plus 3, followed by a few drops of potassium thiocyanate. Use information in table 3 to describe any observations after each addition and explain your answer. So they added at the beginning few drops of the potassium fluoride. So we have to look at the stability constants of each of the complex hexaaqua iron 3 and the other complex where the fluoride is formed. We'll see that the stability of this complex is greater than the stability of the hexaaqua iron 3 complex, And this means that since this is colorless and this is violet, we started with this. We started with the FeH2O6 positive and reacted with the fluoride, with the potassium fluoride. And so it will form the FeH2O5 fluoride 2 positive. And that's because we have seen that the stability constant here is greater than the stability constant here, which means that the complex is going to be formed. And this means that the violet color of the hexaaqua iron 3 will change to colorless, which is the color of the new complex. And then they said that they added excess of the thiocyanate ion. They said here that followed by a few drops of potassium thiocyanate. Now, when they add few drops of the thiocyanate, nothing will happen because as we see here, that the stability constant of the fluoride complex is greater than the stability complex, the stability value of the key stability value of the thiocyanate ion. So this means that the thiocyanate cannot exchange its place with the fluorine because the stability constant of the fluorine complex is greater than that of the thiocyanate complex. So no reaction will take place. And this means that there will be no change in color in the second. No change in color happens when we add drops of the thiocyanate to this complex. So at the first case, the violet color changed to colorless because we see that the stability constant of the fluorine complex is greater than that of the hexaaqua iron 3 complex. So since the stability constant is greater, this means that this complex is going to be formed when this hexaaqua iron 3 reacts with the potassium fluoride. So the color will change from violet to colorless. But as the stability constant of the fluoride complex is greater than the stability constant of the thiocyanate complex, so this means that no reaction will take place when we add potassium thiocyanate to the fluorine complex. Now, they said that hydrated compound J K3FeC2O4 3.x water contains the green complex FeC2O4 3-3. The value of X can be determined by titration of a sample of J with acidified potassium manganate ions. Manganate ions oxidize the ethane diuate ions in acidic conditions according to this equation. Write half equations for the oxidation of the ethane diuate ions and for the reduction of the manganate ions. So for the oxidation of the C2O4, 2 minus, it will change to, as we have seen here, to carbon dioxide. But the first thing that we have to see that here we have 2 carbons, so we have to put here 2 carbons, and we calculate the oxidation state of the carbon here. It's -8, and 2 carbons will be +6. And for 2 carbon dioxide, each carbon will be +4, which means that both will form +8. And so the +6 changes to +8. This means that it will lose 2 electrons to form the carbon dioxide. And no other balancing is going to happen because here we have 2 carbons and 4 oxygens at both sides. For the reduction of the MnO4 minus, it changes to Mn2 positive. So here, when we calculate the oxidation state of the manganese, it's -8 here for the oxygens. It is +7, and here it is +2, which means that it gained 5 electrons to change from +7 to +2. Now we have to balance here. We have 4 oxygens on the left-hand side. We have to add 4 H2O on the right-hand side to balance the oxygen. And then now we have 4 H2. This means that we have to add here 8 H positive. So these are the 2 half ionic equations. And as you see that as these are going to be added together, the number of electrons here and there must be the same. And that's why we have to multiply the first equation by 5. So that's why we get here 5. And we multiply the second equation by 2, so that here we have 2. And we have 10 electrons in both to be cancelled. Now, the said student prepares a solution containing 0.1 gram of J. The student titrates this solution with 0.02 mole per decimeter cube acidified potassium manganate. The titer obtained is 12.2 centimeter cube. Assume all the ethane diuate ions are oxidized. Calculate the value of X in K3FeC2O4 3.X water, and give your answer to the nearest whole number and show your working. And they gave us the molecular mass of the K3, it's 437.1. So as we all do, whenever we have a titration, we have to get first the number of moles of the potassium manganate by which we titrated the ethane diuate ion. So the number of moles of the manganate ions will be the concentration, which is 0.02, times the volume, which is 12.2 over 1,000. And so we get we get 2.44 times 10 to the power minus 4. So this is the number of moles of the manganate. And so from the mole ratio between the manganate and the ethane diuate ion, the mole ratio is 2 to 5. So if we get the number of moles here to be 2.44 times 10 to the power minus 4, so what will be the number of moles of the ethane diuate ions? It will be equal to 2.44 times 10 to the power minus 4 times 5 over 2. So I got 6.1 times 10 to the power minus 4. So we got the number of ethanoate ions. Now we see that every mole of K3FeC2O4 3.X water contains 3 moles of the ethane diuate ions. So this means that if we got the number of moles of the ethane diuate ion to be 6.1 times 10 to the power minus 4, so to get the number of moles of the potassium FeC2O4 3.XH2O, the number of moles is equal to this value divided by 3. So it's 6.1 times 10 to the power minus 4 divided by 3. And so we get 0.0002 moles. So this is the number of moles. And they gave us the mass. So from the number of moles and from the mass, we can get the molar mass of this compound, which is the mass over the number of moles. So the mass is 0.1 gram divided by the number of moles, which is 0.002. So the molecular mass will be it will be 500. The molecular mass will be 500. And so they said that the molecular mass of only this part is this value. So this means that the molecular mass of X water is equal to 500 minus 437.1. So I got 63. So this means that X equals 63 divided by 18, which is the molecular mass of water. I got 3.5 moles. So we have 3.5, or else, yani maybe, let me check for the calculations once more. So 0.02 times 12.2 divided by 1,000. I got 2.44 times 10 to the power minus 4. This is for the manganese, so we multiply by 5 divided by 2. I got 6.1 times 10 to the power minus 4. From the mole ratio, it will be divided by 3 to get. So 0.002. This is the number of moles. Number of moles equal mass over molar mass. So the molar mass equal the mass over the number of moles. And the mass is 0.1. It's 0.1 gram. So I got 491. It's different. Now I got 491.8. So I got 491.8. And so if we subtract this minus 437.1, I got 54.7. If we divide it by 18, so I got 3 moles. I get 3 moles, so X equals 3. Okay. When we look at number 4, it says state the difference in the basicities of ammonia, propanamide, and propylamine, and explain your answer. We have to start with the weakest base first and then the strongest. Then the weakest will be the CH3, CH2, CO, and H2, propanamide, and then followed by the ammonia. And the strongest base will be the propylamine, CH3, CH2, CH2, and H2. Now, to explain this, we are going to say that comparing, of course, the propanamide with ammonia. So in propanamide, there is an electron withdrawing group. There is an electron withdrawing group which is the C double bond O beside the NH2, which decreases the electron density, on nitrogen, making it less easier or less susceptible to attract H positive ions or acids. But in the propylamine, the propyl group is an electron releasing group by positive inductive effect, which increases the electron density. I'm going to write here, which increases the electron density on nitrogen, making it more easier, more susceptible or more easier to attract or accept a proton, because we know that bases are proton acceptors and acids are protons donor. So as we see that here, the CO group is an electron withdrawing group, and so it will withdraw the electrons away from the nitrogen, and so the nitrogen now will have a deficiency of electrons, and this means when it is compared to ammonia, which has its lone pair of electrons present on the nitrogen, and in the propanamide, the electrons are withdrawn from the nitrogen, and so you will see that the electrons on the nitrogen will be lower than the electrons the electron density will be lower than that in case of ammonia, and so it will be less attracting to the protons, whereas in the propylamine or propylamine, we see that the propyl group is an electron releasing group by positive inductive effect, and this will increase the electron density on the nitrogen, and so it will have more acceptability to attract a proton. We come to B. It says figure 4 shows 2 different ways to synthesize propylamine. So in the first one, K, in presence of ammonia, we produce the CH3, CH2, CO, and H2, and then in presence of reagent M, it will change to CH3, CH2, CH2, and H2. And here we have the bromoethane in presence of the potassium cyanide in ethanol. It will form a compound which also with reagent M will form the propylamine. Now they said identify compounds K, L, and reagent M. So here the K is, you see that the difference between ammonia and this compound is this part. And this means that we have here for the K, CH3, CH2, CO, and we know that the acyl chlorides, here we have propanoyl chloride, the acyl chlorides, always when they react with anything, HCl is removed, and the CO, the carbon bonded to the oxygen, will bond to the other reagent that it is reacting with. So here we have the CH3, CH2, CO, Cl. Now for L, when we add the bromoethane to potassium cyanide dissolved in ethanol, we get the propyl nitrile. We get the propyl nitrile. Only the cyanide group exchange place with the bromide. This is nucleophilic substitution. And then what is M? M is a reagent that when it is added to CO and H2, it will form the CH2 and H2. And this means that we can add lithium aluminum hydride, which is a reducing agent in presence of dry ether. And so we will reduce the C double bond O into a CH2. Also here we can, for the cyanide, we can also add lithium aluminum hydride, or we can add hydrogen in presence of nickel or platinum as a catalyst. In C, it says compound N is shown in figure. This is compound N. Compound N is treated with an excess of concentrated hydrochloric acid, aqueous, and undergoes complete hydrolysis to form 3 organic products. The products are isolated from the reaction mixture at pH 4. It means that the solution is acidic. Draw the structures of the 3 organic products at pH 4 and assume that the CH3O group does not react. So we know that when we make hydrolysis, then the bond between the NH and the C double bond O breaks. And since it is present in excess of concentrated hydrochloric acid, so the first organic compound that we are going to get will be here an NH2 positive, because it should form NH2, but in presence of an acid, as the NH2 group is, as the NH group, it will form NH3 positive, because it will form at the beginning NH2, but since the NH2 in presence of the acid medium will form the salt, which is the NH3 positive. And the second part, we will have here the carboxylic group. So here we will have double bond O, OH, because the hydrolysis means that you add here a hydrogen and here an OH. So it will be COOH, and of course in concentrated HCl, nothing will happen here at this part. And we have this part did not change. And then we have here also, it should have been NH2, but of course it will also change into NH3 positive. And for the last one, we will have a CH3 double bond O, and here we will have the OH group. So it will be ethanoic acid. Okay. D says compound P can be synthesized from 1-methyl-4-nitrobenzene, 1-methyl-4-nitrobenzene by the route shown in figure. So 1-methyl-4-nitrobenzene in step 1 gives this compound, in step 2 gives this, until we reach compound P. They said step 1 is a reduction reaction. Complete the equation for this reaction. Complete the equation for this reaction to use H between brackets to represent an atom of hydrogen from the reducing agent. So here we started with the C7, H7NO2. So we start with C7, H7NO2. And now we have to add hydrogen between brackets to produce, here we have C7, H, how much? Here we have 1, 2, 3, 4, 5, 6, and 3 makes 9. N, or we can write it C7, H, 1, 2, 3, 4, and we have 3, 7, and then we have to put NH2, and we have to add water. So as you see that here we added 2 hydrogens, and these 2 water molecules are formed from the 2 oxygens that came outside from the NO2. So this means that here we have 4 hydrogens and here we added 2. This means that we have to put here 6 hydrogen between brackets. Now they said complete table 4 to give details of each step of the synthesis shown in figure 4.3. In step 1, which is the reduction, what are the reagents and conditions? We know that to change the NO2 group to NH2 group, we have to add tin, which is the reducing agent, with concentrated HCl and heat. So these are the conditions and reagents and conditions. We have to add tin, concentrated hydrochloric acid and heat to get this reduction. In step 2, we have the NH2 group changed to NCH3 2. So this means that we added 2 moles of, we know that if you have a halogeno alkane and you reacted with ammonia, so you get CH3NH2 plus HBr. And if you add excess of this molecule, then you will get the NCH3O2. Every time a hydrogen is removed from the nitrogen. So here, the reagent that we are going to use is a halogenoalkane. We can write excess of the halogenoalkane so that we can get the NCH3O2 between brackets. And what are the conditions here? We have to react it in presence of ethanol, because the halogenoalkane must dissolve in ethanol. And also we have to heat under pressure. We have to heat under pressure, or just say heat. So here the reagents and conditions will be excess of CH3Br or Cl and heat, and dissolved in ethanol. So here first dissolved in ethanol, and heat. Now, what is the type of this reaction? So here it will be a nucleophilic substitution. It's going to be nucleophilic substitution. Okay, the third one, in step 3, they changed the CH3 group to COOH group. So this means that this is oxidation. And of course, we do this with potassium manganate. So here we are going to write here the type of reaction is oxidation. And here we have to add cold alkaline potassium manganate. For the last reaction, which is a condensation reaction, we have to change the carboxylic group into this group. So as you see that this is an ester, and this means that we added this part, addition of the alcohol, which is OH, and then we have 1, 2, 3, 4, and here we have a methyl. So we have to add, this is 1, 2, 3, so 3 methyl. We have to add 3 methyl, butane 1-ol to the carboxylic group. And so we will get the ester that they want, and this is a condensation reaction, as they said. Let's see number 5. It says cumene is an aromatic hydrocarbon used in the synthesis of other useful chemicals. So this is the cumene. Complete table 5 to show the number of sp2 and sp3 hybridized carbon atoms that are present in a molecule of cumene. For the sp3, we don't have except these two, because we know that sp3 means that the carbon is, the central atom is bonded to either 3 bonds or to 2 bonds and 3 to 4 bonds, or to 3 bonds and 1 lone pair. So if we look at these 2 carbon atoms, they are bonded to 4 bonds, 3 with hydrogens and 1 with this carbon, and here the same. So for the sp3, we have only 2 carbon atoms that are forming the sp3. Here we have this carbon is bonded to a hydrogen, and also then this will be 3. This will be 3 because also this carbon is bonded to 3 carbon atoms and 1 hydrogen, so it's also sp3. So these are sp3s. The ones in red, they are sp3s. Now let us look at the sp2. Whenever we have a carbon that is bonded to 3 other bonds, so here this carbon is bonded to a carbon 2 and 3. So this means that it is sp2 hybridized, and all the others will be the same, because every carbon here is bonded to a hydrogen and 2 other carbons. Every carbon is bonded to a hydrogen and 2 other carbons. So always there will be sp2 hybridization, and this means that we have 6 sp2 hybridized carbon atoms. So we have 3 sp3s and 6 sp2s. They said here cumene can be synthesized via a Friedel-Crafts alkylation reaction as shown in figure 2. So the benzene plus CH3, CHBr, CH3 gives the alkyl benzene plus hydrogen bromide. Name the mechanism involved in the Friedel-Crafts alkylation shown. So this is called electrophilic substitution reaction, as one of the hydrogens of the benzene was substituted by the alkyl group. The first step of the reaction forms the CH3, CH2, CH positive cation. Identify a suitable reagent for the formation of this cation from 2-bromopropane. So it's the catalyst, aluminium chloride, or we can say aluminium bromide. So this is the catalyst used. Or we can use iron bromide. Now it says complete figure 5.3 to show the mechanism for the reaction between benzene and the CH3 CH positive cation. Include all relevant curly arrows and chars. So here we have to draw a curly arrow from the ring in the benzene to the CH positive that carries the positive charge. And so the intermediate, we are going to draw an opened half circle pointing to the place where this group is going to bond. And then we are going to draw an arrow from the bond between the carbon and the hydrogen to inside the benzene ring to get this one and a hydrogen ion. They said the Friedel-Crafts alkylation of benzene by 1-bromopropane also produces cumene as the major product. The CH3, CH2, CH2 positive cation formed in the first step quickly rearranged to form the CH3O2 CH positive cation. Suggest why this is the case and explain your answer. So we say that as secondary carbocations, are more stable than primary carbocations. So that's why the CH3, CH2, CH2 positive, which is a primary carbocation, rearranges to the CH3 to CH positive secondary carbocation. Here it says cumene oxidizes in air to form phenol and propanone. The delta H naught is minus 371 kilojoules per mole. Table 5 gives some relevant standard entropies for reaction 1. Calculate the standard entropy change, delta S naught of reaction 1. So we know that delta S naught is equal to sigma delta S for entropies of products minus sigma entropies of reactants. So here for the products, we have C6H5OH146 plus the propanone, which is 200, minus 278, plus oxygen, which is 205. So I got 2000. No, I think that there is something wrong. Let me do it again. So here we have 3, 4, 6 minus. Here we have 8 and 4. So 3, 4, 6 minus 483. So I got minus 137 joules per Kelvin per mole. So this is the delta S equal minus 137 joules per Kelvin per mole. They said show that this reaction is feasible. They said show that this reaction is feasible at 25 degrees Celsius. So to show that this reaction is feasible, we have to find out the delta G, which is equal to delta H minus T delta S. And so the delta H here is minus 371 minus the temperature should be in Kelvin. And so we change to Kelvin by adding 273. So it is 298 times the delta S, we have to change it into kilojoules. So it's minus 0.137 kilojoules per Kelvin per mole. So minus 0.137. So we get so this is times 298. So I got minus 330. 0.175. So it's minus 330.17 kilojoules per mole. And so since they said show that this reaction is feasible, so since we got the delta H in a negative value, so here we calculate the delta H, delta G, and we say that since delta G is a negative value, so the reaction is feasible. Here they said figure 5 shows two reactions of phenol. Phenol in case of bromine gives reaction 2, and if we add R and sodium hydroxide reaction, we get this azo compound. So they said, state the conditions for the bromination of phenol in reaction 2, and explain why these conditions are different from those for bromination of benzene. The conditions here is at room temperature. The bromine is aqueous. The bromine is aqueous, not liquid as in case of bromine, and room temperature. And explain why these conditions are different from those for the bromination of benzene. It's because phenol contains the lone pair of electrons on the oxygen. We can say here that the explanation is that the lone pairs of oxygen, the lone pairs of oxygen of the OH group are delocalized, with the 6 pi electrons, on the benzene ring. The electron density on benzene increases, on the benzene ring increases, so more easier to be attracted, so more easier to be attacked, how to react with electrophiles. So we know that the lone pair of electrons here on the oxygen of the phenol can be delocalized with the pi electrons on the benzene ring. And so this means that the electron density on the benzene ring of the phenol, the electron density increases. And so it will be more susceptible to be attacked by electrophiles. They said, draw the structure of the organic compound Q. So here for the Q, we are going to draw the phenol itself. And then we add 2,4,6-tribromo phenol. So this is the 2,4,6-tribromo phenol, which is a white precipitate. And as we know that this is a test for phenols. Type, identify organic reagent R. Identify the organic reagent R. So as we see that the R will be this part because this is the phenol that we started with, and the R will be the benzene diazonium ion. So we draw N triple bond N, and we put the positive charge on the nitrogen that is next to the benzene. So they said, identify the organic reagent R. So this is the R. Okay, we can write here chloride because we know that it's benzene diazonium chloride. This is benzene. And now they said, name the functional group that is formed in reaction 3. We know that this functional group is called the azo group. This is called the azo group. The reaction of phenol with nitric acid produces a mixture of isomers with molecular formulae C6H5NO3. Identify the 2 isomers that are produced in the largest quantities. So here, as we have a phenol, and we know that the OH group directs the incoming groups to the 2 and 4 position. So this means that these are the 2 isomers that are going to be formed when the nitric acid reacts with the phenol. And They said explanation. We say that as the OH group of the phenol is 2,4 director to the incoming group, or we say that it directs the incoming group to the 2,4 positions. We can say it directs the incoming group to the 2,4 positions. We come to question 6. It says malic anhydride is an unsaturated cyclic compound used in the formation of several polymers. Malic anhydride can be used to form malic acid and tartaric acid. Malic acid reacts with ethane 1,2-diol to form a condensation polymer. Draw a section of this polymer showing only one repeat unit. The new functional group formed should be shown fully displayed. Now, if you have malic acid, which is this one, you have a COOH here and another COOH here, and you start with N of it, and you reacted with ethane 1,2-diol. It means that you are having this molecule. So we know that always the hydrogen goes out from the OH, and the OH comes out from the carboxylic group. So this means that the polymer that is formed is going to be the C double bond O, and then you have a double bond here, and then you have a C double bond O. Of course, we don't have to write the C double bond O. We are going, they said show it. So we have to put C double bond O, and then we have an O, which forms with a CH2, and then an O, and you put brackets, and you write N. So they said draw a section of this polymer showing only one. So the carbon of the C double bond O will bond to the oxygen of the ethane diol. And so we will have a CH2O, and then we extend the C double bond O and the O to form the polymer. Identify a suitable reagent and conditions for reaction 2. Reaction 2 change the double bond to two OH groups. So here we add cold potassium manganate, so that it will form the diol, and in presence of phosphoric acid as a catalyst. Identify a suitable reagent and the conditions for reaction 2. So we add cold potassium manganate and phosphoric acid as a catalyst. Taban, if we add hot potassium manganate, it will break the C double bond C. Now, they said compound U can be formed from tartaric acid in 2 steps as shown in figure. So in the first one, they added propanone and H positive in step 1, and then in step 2, it produced the compound U. Suggest the type of reaction that occurs in step 1. So as you see in step 1, what happened is that a water molecule is removed, and also the propanone is added. So this is either we say addition, elimination. So here, as you see, this is the carbon. This is the carbon of the propanone, and these are the 2 CH3s. So there is a water removed. So this is either we say condensation, or we say addition, elimination. Because the water molecule is eliminated, 2 hydrogens, and the oxygen, one of the oxygens, and 2 hydrogens were removed as water, and the propanone was added. U can act as a bidentate ligand. Explain what is meant by bidentate ligand. It is species that can donate 2 lone pairs to a metal ion, 2 lone pairs of electrons to a metal ion, forming 2 dative bonds. Forming 2 dative bonds. It is a species that can donate 2 lone pairs of electrons to a metal ion, forming 2 dative bonds. Of course, 2 lone pairs of electrons from 2 different atoms. From 2 atoms. Because sometimes an atom can have 2 lone pairs of electrons, it cannot donate both. It donates only one, and another atom will donate the other. Now, complete the 3-dimensional diagram in figure 6.3 to show both stereoisomers of copper U3 minus 4. Of course, we have to draw it in the 3-dimensional structure. So we draw wedges and we draw the dotted lines. And here we put O to represent this ligand. And the other one, of course, we have to put the minus 4. And here we will do the same, but it will be a mirror image because this is an optical isomer. So here we draw it as a mirror image of the other. And we draw the charge, minus 4. Now they said the student analyzes an aromatic compound X, C8H8O3 using NMR spectroscopy. Figure 6.4 shows the carbon-13 NMR spectrum of a sample of X dissolved in D2O. Separate samples of X were analyzed. So we have C8H8O3. And in carbon-13, it has how many peaks? 1, 2, 3, 4, 5, 6, 7, 8. So it has 8 peaks in the carbon-13. This means that it has 8 carbons with different environments, 8 different environments for the carbons. Separate samples of X were analyzed using the proton NMR spectroscopy. Table 6 gives information obtained from this analysis using the deuterated chloroform. We got 6 peaks for the protons, 6 signals. And in presence of D2O, it formed 4, which means that we have 2 OH groups, because we know that when we use the D2O in the proton NMR spectroscopy, the OH groups, NH groups, the hydrogens are going to be substituted by a deuterium, and then it will not show a signal for its proton. Whenever we have an OH or an NH, and we add deuterium oxide, so due to the exchange between the deuterium and the hydrogen atom, so here we will get an OD, and here we will get an D2, and this means that these deuterium atoms are not going to absorb in the NMR, and so we will not get any peak or any signal for them. So here, since they used the deuterium chloroform, the deuterated chloroform, and they got 6 signals, and then in presence of D2O, they got 4. So this means that here we have 6 proton, 6 hydrogen environments, and 2 of them are OH. 2 of them are OH groups. Now they said identify the number of different carbon environments present in X. So as we said here, as there are 8 peaks, then we have 8 carbon environments, 8 carbon different environments. We have 8 carbon different environments. Now explain why X is dissolved in deuterated oxide before obtaining its proton NMR spectrum to test for the presence of the OH group as it disappears, as its signal disappears in G2O. Okay. Now they said aromatic compound X they said that aromatic compound X gives a yellow precipitate when it reacts with alkaline iodine. So we have here aromatic, and we have that it gives a yellow precipitate with the alkaline I2. It means that it contains the group, which is the CH3, contains the CH3 C double bond O group, and use the information in C to suggest a structure for X, and explain your reasoning. So they give us the carbon-13 NMR chemical shift range. So the first thing that we see that here in the carbon-13, we have a peak at about 60, 62, something like that, 61, 62. So when we look here at the carbon compounds, we see that the carbon-13 NMR, we see that if we have a carbon atom that is next to a carbonyl or a carboxyl group, then it will have a peak between 30 and 65. Or if it is a carbon next to a halogen, we don't have a halogen here, so we are not going to consider this. So this means that the first thing that we have a peak at delta equal 61 part per million is due to a carbon that is next to a carbonyl, carbon next to carbonyl, or a carboxyl, COOH. Okay, and then we have here a peak at between 200 and 220. It's about 204 or something like that, 203, 204. So we have another peak at 200 and about 3, 4 part per million. So we look at this range, 200, it's here, carbonyl, it's a carbonyl group. If it was a carboxyl, because here they said it's a carbon next either to a carbonyl or carboxyl. If it was a carboxyl, then our peak should appear between 160 to 185, but we got one at 204, so this means that this is a carbonyl carbon. And then we have other peaks between 110 and 160. We have 1, 2, 3, 4, 5, 6 peaks at delta between 110 and 160 part per million. We have 6 peaks. So we see that between 110 and 160, we have the peaks of alkenes or arenes. Arenes, because they said that we are having an aromatic compound. So this means that these 6 peaks are present in the benzene ring, because at the beginning they told us that our compound is an aromatic compound, right? They said aromatic compound X. So now they want us to draw the structure of X. They said that it is aromatic. It means that we have to draw a benzene, and then it should have a group which is the CH3CO group. So we have 8 carbons, so we can write a C double bond O CH3. So we have this group that will result in the formation of the yellow precipitate. And then we still have, now if we count the number of carbons, they are 8, but the hydrogens here we have 1, 2, 3, 4, 5, and 3 makes 8. But the oxygens are only 1, and we want 3. And we said that when we have 6 protons and 2 of them were removed when we added the D2O, the deuterated oxide, this means that we have 2 hydroxide ions. So we can draw one of them, for example, here, let us try, yani, and the other here. So will this make 8 carbon environments? So this is 1, 2, 3, 4, 5, 6. We have 7 and 8. So now we have 8 carbon environments. And we have a carbon that is next from the proton NMR. We have a carbon. No, sorry, from the carbon 13, we have a carbon next to a carbonyl. And we have the carbonyl. So here, if you look, we have 8 carbon. We have 8 carbon 13 environments. Now, what if I draw it in this way? C double bond O, CH3, and I put the OH here, for example, and here. So now we will not get 8 carbon environments. Are we going to get it? 1, 2, 3, 4, 5. This is between 2 COH, 6, 7, and 8. So we also can get 8 carbon environments. Here we can get 8, and here we can get 8. Because here, when we look at this carbon, it's different from that, because it is bonded to a C, bonded to a C double bond O. When we look at this, it's different. Here we have a different carbon because it is bonded from one side to the carbon OH and from the other side to CH2. So it's different from them. This one is bonded to a carbon that is bonded to a COH, and this is bonded to a CH2, but to a C double bond also it's different, and that's it's different. When we look at this structure, we see that this carbon, of course, is different than the 3 others. If we look at this, it's different from that, different. And this one is also different from the others. So you can draw either this structure or that structure. Both are correct. So what about we look at the protons, come on. We have to look to the protons. From the carbon 13 point of view, both structures can be correct. So what about the hydrogen environments? We said that 2 of them are removed because we have 2 OH groups. So these are containing 2 OH groups. Now we have to find out 6 proton environments. So if I write A for the protons, this carbon doesn't have any proton. This will have a proton, which is different than that. Now for the protons here, we have 1, 2, 3. There is a proton here, a proton here, a proton here. So here we have C, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 6 proton environments. Here also we have 1, 2, 3, 4, 5, 6. So both of them can produce also 6 proton environments. So this means that you can draw either of these 2 structures. you can draw either of these two structures because both have 8 carbon-13 peaks and 6 protons in their environments. Right. Okay, so we can draw any one of them. Okay, thank you so much for your attention and best of luck in your exam.